Welcome to the online causal inference seminar. Today we have Yiqing Su and Jin Pang talk about a Bayesian alternative to synthetic control for comparative case studies, a dynamic multi-level latent factor model with hierarchical shrinkage. They will also stop from time to time to take questions from the audience, so please submit your questions via Q&A. As a discussant, we have Dmitry from Madrid, and he will give a short 5 to 10 minute presentation. After that, Yiqing and Jin will have the opportunity to respond, and then we will take some more questions from the audience if we have time. The questions today will be handled by Guillaume, so I'm now switching over to him.
Thank you, Dominic. So as Dominic said, the questions will be handled through the Q&A. So we don't have a collaborator today. So I will basically just select questions and ask them to Yiqing and Jin when they stop. So please ask them through the Q&A. If your question is selected, I will reach out to you via chat to ask you if you're comfortable asking the question live. And if you are, I'll ask you to raise your hand. So please don't raise your hand until I've asked you to do so. All right, that's basically it from me. Yiqing, whenever you're ready, or Jin, whoever is starting first. Thanks.
All right, I guess I'm can you hear me? Okay, so my name is Yiqing Xu. I'm from Stanford Political Science Department. Xu and I are extremely honored and happy to be able to get this opportunity to present recent work, extremely preliminary work to this fantastic audience. This is also collaborated with Lichen Liu from MIT, who's now a graduate student. Our talk today is about a Bayesian alternative to synthetic control for comparative case studies. So since
Sorry, we can't see your video stream currently. Did you turn it off?
You cannot see my video? You mean my person?
No, I can see it. Sorry. Yeah. Okay. Yeah, now I can see.
So the slide is fine?
Yeah, slide is fine.
As well?
All good.
Oh, yeah. Run the presentation mode. Since the innovation by Abadi and co-authors on the synthetic control method, comparative case studies have become increasingly popular in social sciences, including political science. I'm from political science. And comparative case studies have some unique features. And these features pose challenges to statistical inference. Abadi recently have a very nice summary in JEL, talk about these unique features. Usually you have one or a few treated units that receive a non-randomly assigned intervention, and those units sometimes are at the aggregate level. So even for the control units, you don't have a large donor pool. And because the treatment is not randomly assigned, oftentimes you have unobserved time varying confounder. That's exactly why people want to use SEM to fix the trend. You're not in a regime of parallel trend, so to speak. Another potential problem is that the treatment effect is highly heterogeneous, both across units and over time. Those interventions takes time to build up. That's why if you assume a stringent model like two-way fixed effects, the model is going to be erroneous. So here's one example, a very famous one by the authors in a 2015 paper in AJPS, where they look at the effect of German reunification on Western Germany's GDP per capita. On the right-hand side, I plot the raw outcome data of 16 OECD countries, including West Germany. X-axis is time, y-axis is outcome, and the treated unit, Western Germany, is in blue. And there it is treated in 1989, 1990 is regarded as the first period of the treatment. So if you look at the treatment status plot, again, the x-axis time, y-axis are the countries. We see there's only one country treated since 1990. In another example is a paper of mine a few years ago where I look at the effect of election day registration on voter turnout. For those who are unfamiliar with EDR, EDR is a policy or institution that allows voters to register on the same day of voting, which is deemed as a way to reduce the cost of voting. People think it can increase turnout, but it's hard to conduct difference type of analysis exactly because the trends are not parallel. If you look at the control groups and the treatment groups, their averages are certainly not parallel. And you have 9 units that have adopted EDR before 2012, where the data ends, and these units start getting treated at different times for different time periods. Okay, so the synthetic control, the invention of synthetic control is a combination of many great ideas. It also has challenges. I think the first important thing, it takes advantage of pre-treatment outcomes, and then exploit, that's I think a very important feature of this method, that exploit cross-sectional instead of time series correlations in data. Hence, because you need to use your neighbor's information in the causal framework, it's not based on sequential ignorability. It's actually based on a more generalized version of parallel trends. That also poses some challenge to identification and inference. It uses a convex combination of donors to construct treated counterfactuals, and those weights are non-negative and added to 1. It has the feature, because of that, it has the advantage of being very transparent and interpretable. You can interpret Western Germany as a combination of other countries like Austria and the United States. It reserves some pretreatment periods for testing. That's a very nice feature, and also propose a placebo type of test for inference. And the inference is not exactly formal because the treatment is not randomly assigned, so you cannot directly interpret the results from the placebo test as a Fisher type randomization test. So the challenges include you deal with 1 treated unit at a time, and inference sometimes is hard if it's not impossible for the reason I just mentioned. And in the second paper, the authors propose a sensitivity analysis, basically what's the probability of getting treatment is different between the treated unit and other units is going to affect the causal estimates. And then user discretions may result in over rejection. This is because you do have some degree of research degree of freedom to choose which predictor to enter your synthetic control. And sometimes it's difficult to find a solution. This is not necessarily a bad feature. If you don't find a good fit in the pre-treatment period, that's fine, because you simply cannot, the data does not allow you to do this research. But it may also exacerbate the publication bias. There are some new developments, actually a lot of exciting developments in the field, including a lot of people in the audience. There are regression methods, including Sheldon and co-authors using best subsetting, and the Chanko and Ingben's paper, which is a nice summary of existing methods using regression and with regularization. And also there are latent factor approach by these 2 authors, and I wrote a paper, and then Susan and Hiro wrote a paper on matrix completion, and by Jushan and Professor Ang wrote another paper just quite recently, also tried to tackle this problem. They also, doubly robust methods try to tackle both the treatment assignment mechanism and the outcome model. Most famously, these two papers. These approaches also have drawbacks. I think the most important one is still inference. Uncertainty estimates are difficult to interpret in a frequentist framework because it's hard to imagine sometimes in a repeated sampling framework of like Western other countries getting the treatment of reunification. It's just simply hard to imagine such a superpopulation. And also a lot of those estimates are based on large sample series. Even you use methods like jackknife, you actually relies on asymptotopia. And simply estimation, some of these methods, estimation require large number of pretreatment periods and a large N, especially the control group needs to be large. And some of these methods needs to choose a tuning parameter, and they often use cross-validation to choose tuning parameter. If you have small data, we know that this is not very reliable. And uncertainties of choosing model is usually not incorporated in the uncertainty estimates if you have uncertainty, if you have them. So there are also some Bayesian development. In this paper, in this first paper by Broderson, I think the disadvantage is that it does not directly take advantage of cross-sectional correlation, which I think is the very important innovation of synthetic control. And the second paper is actually very related to our talk today, but its disadvantage is that it does not incorporate information on the covariates, and the allocation assumptions are not explicitly made. So today, our goal is to provide valid, we hope to be valid Bayesian inference for both individual and average treatment effects in comparative case studies. It's average when you have more than one treated unit. It's a full Bayesian approach, including theory, estimation, prediction, and inference based on MCMC. Several key features. First, it's full Bayesian, and we treated counterfactual as missing data under the missing not and random framework according to Rubin. And the inference is completely based on posterior distribution of imputed counterfactuals. And it's also semi-parametric in the sense that we incorporate the multi-factor state space model and model averaging with stochastic model specification search. With the factor analysis, we also impose sparse modeling with Bayesian lasso to shrink both the factor loadings and also coefficient for the covariates. You can put in a lot of observed covariates and then let the model to figure out which of the covariates and factors are important. It takes 3 simple steps. First step is to use the non-treated data. I'll explain what that means. With the MCMC approach, let's say this is the example I gave you early with the election day registration. But what we use is those not in gray, but in blue. Those are non-treated observed outcome. And then once we have the sort of model, we make Bayesian prediction for those under treatment condition. Then we summarize an average. And the main contribution of this paper, I think, is first to clarify the assumptions needed for causal inference, Bayesian causal inference for this particular type of studies. Second, we try to address inferential problems for comparative case studies when you only maybe have one treated unit. Third, we try to avoid as much as possible ad hoc modeling choices, including choosing covariate and number factors. 4, it's a model-based approach, but we want to make the model more flexible and hopefully more efficient. Last but not least, we develop an open source software in R for implementation. It's written in C++, so it's fairly fast to implement with not too large data sets. Okay, so next I'm going to talk about the basic idea behind posterior predictive inference. Then my colleague Shrink is going to talk about the details of the model, and then 3 examples, including one simulated example, and then we're going to conclude. First, I'm going to talk about posterior predictive inference. Let's fix the notation first. We have n units and t time periods. It's a balanced panel, but our methods can very easily accommodate imbalanced panel. Just treat the missing data as missing in the Bayesian framework. The first assumption is that we follow the stack adoption design in Sudan and Hido's paper. We define AI as a time adopting the treatment for unit I. So the entire treatment vector is determined by this scalar AI. And when AI is infinite, unit I never adopts treatment, and we call this type of unit the control units. So the treatment assignment vector essentially is determined by AI, And if we collect all of them in W, W is the treatment assignment matrix. So Yi is a vector of outcome, observed outcome for unit I. And we have this assumption 2, which is SUVA across unit. This assumption says basically for each unit, your potential outcome is only going to be affected by Wi and only affected by AI, but not other people, your neighbor's potential outcome. But here we do allow a carryover effect. We allow the treatment start like gradually take over. It doesn't have to be, the treatment effect doesn't have to be contemporaneous. We denote the number of control units N1 and the number of treated units. Here, the treated units means that during the observed time window, as long as the unit is treated for one time period, it's called the treated units, and their summation is n. And the number of control units is much bigger than the number of treated unit. So we also have some observed covariates. These covariates can be time varying or can be time invariant. Doesn't matter in the Bayesian framework. And we put all the timing together. We call this A, the adoption vector. We also write this non-treated potential outcome matrix M by T as a combination of the observed outcome and the missing outcome. The reason why we wrote this is because later on we're going to make predictive posterior predictive inference for the missing potential outcome. Once we have the missing non-treated potential outcome, we take a difference, we do summarization, and we can have the inference for the treatment effects. Okay, to simplify notation, because of SUVA and because of staggered adoption, the potential outcome can be simply written as YIT0 and YIT1 without loss of generosity. And then we define causal quantity of interest as a difference between these two numbers. Delta IT can be arbitrarily heterogeneous. Y1 is observed, and YIT0 is the counterfactual outcome, which we are interested in. And then we can also define average treatment effect on the treated that have adopted treatment with a duration for P periods. And researchers can, where here the MP is the number of units that have adopted the treated for P periods. We do this because the applied researchers often like to draw this, people call dynamic treatment effects plots, where they look at how the treatment effects evolve over time. Researchers can also define other estimates of interest or other ways of grouping. In the literature, there are people looking at the average cohort treatment effects. The cohort is defined by the timing, by AI, essentially by the timing of adoption. All right, under assumption 1 and 2, SUVA and stack adoption, we can write this is the treatment assignment mechanism. Sorry, yes, this is W essentially is A. We can simply simplify this one to Y0 because all the information of AI reasonably can be incorporated in the non-treated potential outcome in the pre-treatment period. And because of the SUVA assumption, we can write them as a product. And then we also assume probability assignment, the probability of getting any AI is between 0 and 1. However, for some of the non-treated potential outcome is missing under the missing not a random framework. The treatment assignment may be correlated with the potential outcome that are missing. That's why we need to make this additional assumption, what we call latent ignorability. This terminology is actually not invented by us. There are other people use this terminology. For example, so essentially what we do is try to break the link between the treatment assignment and unobserved potential outcome. What we do is to put in this this random variable or unobserved variable UI. Here we treat it as observed. When we condition on this UI, the treatment assignment essentially can be written as conditioning on observed covariates and observed pre-treatment outcome and this UI. In the literature, this UI is used for example, the principal strata, but here it's for another purpose. The direction here is that we want to learn UI's distribution from observed data, including covariates and including non-treated potential outcome. And then once we learn their distribution, we integrate them out, and then the treatment assignment will be ignorable as expressed by this equation. But in order to do that, the UI cannot come from nowhere. In order to do that, we need to learn UI from data. That's why we have this fourth assumption, which we call feasible data extraction. So UI can be approximate. UI is an n by t matrix, can be approximated by two lower rank matrices, factor and their factor loadings. This assumption is actually explicitly or implicitly made in the factor analysis, in the factor augmented model literature. Like in Sudan and Calder's papers, they do not directly look at factor and factor loading. They look at a lower rank matrix L that can approximate U. It's a similar idea. So essentially, we want to use data that have some missingness, but we are able to approximate this U with a lower rank matrix or two lower rank matrices. Okay, so once we have these four assumptions, this is our target. Our target is the posterior predicted distribution of Y missing, the counterfactual, conditional on treatment assignment, observed Y, and covariates. Then we write it using the Bayesian rule. It's proportional to the joint distribution of observed covariates and non-treated potential outcome. Here, there's some missing data. We don't observe all of them. That's the issue we need to tackle. And then the treatment assignment mechanism. So the first part is what people call underlying science or the model. And the second part is the assignment mechanism. And we can write X prime as observed data and this U, this latent variable. And because of the latent ignorability, we can rewrite this term as proportional to the new science, the joint distribution of non-treated potential outcomes relationships. There is just a distribution with both observed variable and the latent variable, as well as this treatment assignment mechanism, because now it's all figured out. This part can be ignored if the distribution of U can be learned from the observed outcome. And then we can write this term as proportional to the first part, essentially the joint distribution of non-treated potential outcome and X prime. So we need to, in order to proceed, we need to make another assumption, which is exchangeability. Here we assume that Y0 and X prime, the non-treated potential outcome, and this observed covariates and this UI and this U, N by T matrix is rho exchangeable. Essentially, there's no additional information needed in terms of their geographic relationship once we have the information, information about U. So once we have that, we can roll this underlying model between the potential outcome, non-treated potential outcome, and the X prime as a integral of the product of two parts. One part, the first part is posterior predicted distribution, and the second part is the likelihood, what we observed. For the likelihood, it's the model for non-treated potential outcome before the treatment kicks in. So with the data, we can update this Y theta prime, which essentially pins down the relationship between the potential outcome and observed covariates and this UI. And this U is here treated as unknown parameters, and then we will be part of the parameter space. And then once we have these parameters, of course, the UI will, in our framework, will be decomposed into factors and factor loadings. So once we have these parameters, we can draw samples based on this model for the missing non-treated potential outcome, or the counterfactual. So that's the general framework of our posterior predictive inference. Here we're going to pause for a little bit, and then Shrin is going to take over to explain the details of the model, and then 3 examples.
Thanks, Yiqing. So one quick clarification. So you mentioned that some of the assumptions that you're making are being made either explicitly or implicitly by other approaches in the literature. One question is, so far, is there anything that's very specific to the Bayesian approach? I mean, apart from obviously the fact that you're looking at posterior inference, but are your assumptions, can your assumptions be used by other methods that are not Bayesian and basically get similar results?
Well, I think some of the non-Bayesian approaches, for example, the ignore, let me see. I think in the frequency framework, sometimes people make even stronger assumptions on the error term. Like they would directly conditional on, they assume ignorability between the potential outcome and the treatment assignment, conditional on factors and factor loadings as parameters, but these parameters are not known. So that's this type of assumption always looks odd to me because we are conditional on something unobserved, but other assumptions are actually already made.
Okay, makes sense. Thanks, Yiqing. I think there are no other questions. So.
And sometimes people make assumptions on the conditional mean, not the distribution for understandable reasons.
Yeah, thanks.
So any other questions? So should I just continue?
No, you may continue whenever you want.
Okay, sure. I need to. I'm trying to share the screen. Okay. I'm trying to find my part. Okay, here we go. So let's continue. So we derived the likelihood and the posterior predictive distribution based on several important identification assumptions and explicate the steps required to make Bayesian causal inference. Now the task is to build a parametric model on likelihood for counterfactual prediction. So assume the data generating process of control outcomes can be represented by this hierarchical model. So XIT here is a set of covariates, and we relate the coefficients of X to vary cross-sectionally and over time. Because we would like to make use of heterogeneous and dynamic relationships in counterfactual construction, and also handle some possible structural breaks. So the multi-factor term is used to approximate the unobserved confounder UI, Yiqing just mentioned, to satisfy the latent ignorability assumption, which is crucial to identification. So finally, we smooth out the time-varying parameters with AR1 process, and both the phi's here, diagonal matrices with autoregressive coefficients on the diagonal. So the coefficients and the factors are set to be dynamic in order to correct for zero correlation and satisfy the conditional exchangeability assumption. So I will talk about how to select factors and determine when to have random coefficients a little bit later. But now let's look at the reduced form of the model. So it can be written like this. And we differentiate the covariates into 3 types, and those with constant relationships with the outcome, those with unit varying or time varying coefficients. So this is only for showing that the researcher has the flexibility to decide whether a relationship between the outcome and a certain covariate to vary or not, as well as how it varies. So this reduced form also reveals the assumption about the variance covariance structure of the composite errors that heteroscedastic and serocorrelated. So the actual covariance matrix should be more complicated like this because we actually do not assume the 3 components are independent of one another. Now we can see that the random coefficients and the factor term are used to extract the correlation and heterodasticity from the composite error and make the idiosyncratic error epsilon here, IID. Finally, the Bayesian framework, we have to make a lot of assumptions about the prior distributions of all the parameters and hyperparameters. We mostly use conjugate priors and make them flat and put shrinkage priors on the factors and the varying parts of coefficients. So our model is linked to several existing methods. So here, because the model is only on control outcomes and the W is 0, so we can add a term delta IT times WIT in the model, and delta IT is a causal effect of unit I time T. Now it's clear to see that DID, the linear factor models, and the factor model based on which the synthetic control method is motivated are all some special cases of the proposed model by imposing some restrictions on covariates or parameters. So the model I just talked about is a general form based on which we do model searching and factor selection to decide what is the exact model we want to use for counterfactual prediction. So there are several difficult decisions to make when specifying such a model. So first, we would like to include a sufficient number of factors and varying parameters in the model to approximate the unobserved confounder U, ensure exchangeability, and construct adequate counterfactuals. Therefore, the factor analysis as dense modeling is applied for data feature extraction and variable aggregation. But factor selection is a challenging problem. Okay. I see the questions. So the second difficult, should I close this? So the second difficult question is how many varying coefficients to be included and for which covariates. So over-parameterization and overfitting will cause poor out-of-sample prediction. So therefore, we use sparse modeling to do shrinkage and variable selection. So there are a lot of Bayesian shrinkage techniques developed and applied in the literature for model searching. But here, okay. But here we use a very simple one, Bayesian lasso, and lasso-like hierarchical shrinkage. So this is a well-known lasso regression, and lambda here is the regularization penalty. Bayesian lasso is to use a Gaussian mixture prior, and lambda here is a shrinkage, is a tuning parameter. So it controls the shrinkage. So the larger the value, the more aggressive the shrinkage is. So we do not make it a fixed number. Instead, we specify gamma prior on lambda. We choose the hyperparameters A1 and A2 to make the gamma distribution flat. So for betas, we can directly apply Bayesian lasso for shrinkage. So However, for the varying coefficients, Bayesian last law cannot be directly applied. So we use a trick, which is reparameterization, and we call it as hierarchical Bayesian shrinkage. So the reparameterization is done like this. So we assume a diagonal variance covariance matrix of those varying parameters, and then take the standard deviation parameter omega out of the covariance matrix and reparameterize those varying parameters. And now Bayesian Nassau is ready to be applied on the invariant part omega of the varying parameters. So straightforward and nothing fancy here, but you might be suspicious now about the method because it's easy to see that omegas and those tilde parameters are not identified. But the thing is, we do not need them to be identified as long as the original parameter and the factors are identifiable. So we just did some like permutation here to ensure omega is symmetrically bimodal with mean 0. But if omega is shrink to 0, then its posterior is unimodal and concentrated around 0. Therefore, a clear bimodal omega means a successful escape from the shrinkage. But the unimodal posterior of omega means that it's shrunk to virtually 0. So with Bayesian last law and the hierarchical Bayesian shrinkage, features in the general form of the model can be mechanically chosen by algorithm and data, including the constant and the varying coefficients and the factors. Importantly, we will do model searching and parameter estimation in the same MCMC sampling process. So in each MCMC iteration, the algorithm chooses to include or exclude some model specification features, and it can be understood as sampling a model from the model space. So the posterior draws of the parameters are actually from a mixture of many models. So now we can have a more concrete idea about how to implement the method for Bayesian causal inference. So first, based on the general model and Bayesian stochastic model searching, we decide the functional form of the posterior predicted distribution from which we generate posterior draws conditional on observed control outcomes and the pre-treatment covariates, and we call it a donor set. Then we plug in the sample of the parameters into the posterior predictive distribution of control outcomes of the treated, and they generate a sample of each counterfactual IT. And then the third step is to compare the observed outcome and the treated observed outcome of the treated with each draw of the predicted counterfactual, and it generates a sample of individual treatment effect of the treated. And then for any other causal estimate, we can aggregate and summarize the sample of delta IT and have the point and interval estimates. So I will show you several examples as promised by Yiqing. So first, let me show you a simulated one. So in this Monte Carlo experiment, we simulated the panel data of 50 units repeatedly measured in 30 periods. 5 units received the treatment at period 21 and stayed treated in the rest of the time here. So the control outcome follows the data generation process like this. One intercept and 4 covariates all have time varying coefficients, and also 2 dynamic factors and plus 2-way fixed effects. So the treatment assignment at time 21 is correlated with the factor loadings here. Like finally, the true treatment effect of the treated is heterogeneous and governed by this process. So this process simply means the expected value of the treatment effect gradually increases as the treatment goes on. So we applied the proposed method and then compared it with DID. So this graph shows the results of DID estimated also using MCMC. So the red dashed line here indicates the true average treatment effect of the treated ATT. So it shows a strong pre-trend, and there are significant effects in quite a few times in the pre-treatment period. In the post-treatment period, we also see significant biases for the ATT almost half of the time. Here we go. So this is what we get by using the proposed method. It performs significantly better. So the ATT estimates in both pre and treatment periods are close to the true value and mostly covered by the 95 credibility intervals. So we put 10 factors in the model for selection. This figure shows that the number of factors is correctly selected by hierarchical shrinkage priors because the posteriors of omega associated to factor number 2 and the factor number 9 are clearly bimodal, showing that the 2 factors escape to shrinkage. And the other omegas are shrunk to virtually 0, had a very concentrated unimodal posterior. So remember that in a true data generation process, the true number of factors is 2. Okay, now covariate selection. Remember in the true data generation process, there are 4 covariates besides the intercept that have non-zero and time-varying coefficients. But we fit the model with non-covariates. Of course, 5 of them should have no influence. So the algorithm correctly detected the 0 and the non-zero coefficients and whether the influence varies or not over time. Okay, so now I go back to the 2 empirical applications each mentioned before as a motivation examples. So first, the famous German reunification example in ADH. This graph is actually from ADH, showing the synthetic controls of West Germany in the pre and post-treatment period. So this one is based on our method. Okay, this one is based on our method. The graph reports the predicted outcomes in the pre-treatment period and the predicted counterfactuals in the post-treatment period. The point estimates we can see look very similar. There are some minor differences, but they're not important. What is important is that we have the Bayesian credibility interval in each year. Also, like in the pre-treatment time period, we also have the Bayesian credibility intervals, and you cannot see it because the intervals are very narrow. And so with the Bayesian credibility intervals of the counterfactuals, statistical inference is ready to make in a conventional way because we can compare the observed outcome in each post-treatment year with the posterior distribution of its counterfactual and get the point estimate and its error bands and make inference about the effect and also its dynamic change. Okay, we also did a placebo test by artificially setting the leading 5 years before the reunification as a placebo period. So this test shows that no significant effect in the years during the placebo period and suggests that our method predicts the non-treatment potential outcomes fairly precisely. Factor selection. we put 10 initial factors in the model. So here are how the factors are selected. Now the results based on this empirical data set are not as clear-cut as in the simulated example. So 4 of the posteriors of omegas have a clear bimodal shape. So the first, the second, the third, and the sixth, and there are associated factors included in the model. Also, a few posteriors are more spike-shaped, though not perfectly unimodal, such as the 7th to the 10th factors. So they're actually virtually excluded. When the algorithm is not very sure, it produces posterior distribution more like this, and then this guy and this guy. So because in some iterations, those factors are virtually excluded, but in others, they escape the shrinkage. So this graph shows the point estimate of the impact of the first factor. So this factor. First factor on outcome of each country. It's clear to see the heterogeneous of the time trends. So the blue line is West Germany. So it has a very different unobserved time trend from some of those donor countries. So here are the results of selection of covariates. So this example is a little bit unique. So all covariates are shrunk to 0. So the time during intercept here, together with the factors, capture almost all the dynamic of GDP per capita change in Germany, probably because the trend is too smooth. So the second empirical example is on the effect of election day registration on voter turnout in Yiqing's previous work. So here we focus on the comparison of uncertainty measurement based on the Bayesian posterior distribution and the parametric bootstrap approach. So we see that the Bayesian 95 credibility interval is much smaller than the frequentist confidence interval generated by the parametric bootstrap. So the error bands in the pre-treatment period are not very different, still different, but the difference is much more remarkable in the out-of-sample counterfactual prediction in the post-treatment period. Okay, so there are at least 3 reasons can explain this efficiency gain. So first, the Bayesian approach uses priors. We use flat priors, but we're not doing all Bayes. So the priors may still inject some information. Second, our model is a hierarchical model, and so parameter estimation can borrow information across groups and increase the efficiency of using information. Also, this is a dynamic model, so the latent factors are dynamic, and coefficients have a dynamic part. So fully modeling dynamic always helps prediction. So finally, let me wrap up by summarizing the strengths and the limitations of the proposed method. So the strengths, I think, mainly from the Bayesian approach, including measuring uncertainty, being flexible in model specification powered by MCMC, making inference without relying on asymptotics, and the efficient Bayesian stochastic variable selection. Limitations. So first, we do not model the treatment assignment mechanism by dropping it out with the latent ignorability assumption. Second, this is a parameter-rich model-based approach, so it's very difficult to know each donor's contribution to counterfactual construction. Third, the model is, again, model-based, and the risk of misspecification is still there, even though we use stochastic model searching to reduce model dependence. The last one is not on the slides, but I want to point out we only consider staggered adoption, and some crucial identification assumptions we made for this method are unlikely to be held in other settings. So that's all. Thank you.
Fantastic. Thank you for the great talk, Jin and Yiqing. We're now switching over to the discussion. We will have Dmitry present some slides, and then we will go back, and Yiqing and Jin can respond if they want. All right, switching over to Dmitry now.
All right, I can start sharing, right?
Yes.
All right, hello everybody. My name is Dmitry. And I want to thank guys for the very nice presentation. I think this is a super exciting topic and a very nice paper. And we know that panel data sets, not only time series cross sections, but also real panel data, they are widely used now and for policy evaluation. So especially when there are no experiments, and most of the work that's done with panel data focuses on the models with latent variables, right? Because that's the key thing to represent an observed confounder. And from this perspective, doing Bayesian, I think, is very natural, right? Because you don't observe something, and can you deal with this without being Bayesian? So it's a very natural approach, but also it's challenging, because what you need to do, it's not only to specify the assignment model, the outcome model, but also the assignment model. And that's typically that's troubling, right? Because we might not know much about the way it's done. The assignment is actually done. And so what this paper does, at least from my perspective, right? So maybe I missed something, but what people are doing in this paper is that they focus on a flexible outcome model, and they use one trick to ignore the assignment model. So here's how I view what's going on. And this is the simplest example. So it's not the model from the paper, it's just something that I came up with to kind of illustrate this problem. So assume that you have just one unit that you observe over some periods, and the outcomes, they are binary. So here you have the baseline that in every period you are the 0 or 1. Then there is treatment that happens after some period T0, and you can be either treated or not. Okay, so this is the only thing that happens. And the thing that drives the outcomes and the treatment assignment is this unobserved UI, right? So in every period there is the UI that's doesn't depend on anything that depends on time. And then there are the shocks that determine whether you're treated or not, and whether your outcome is 0 or 1. Okay, so in this model, we do not observe the baseline once you get treated. So we want to make posterior predictions about it. And so if you look at this, it's clear that the posterior depends on the whole history of the outcomes, but also depends on DI, right? So you need to know the assignment model to make the posterior imputations that are fully Bayesian in some sense. And that dependence on DI, it's there, but it's weak, right? Why is it weak? Well, in this very simple model, observing DI is essentially equivalent to observing one additional time period, right? Because on every outcomes are binary, this thing is binary, all these errors are independent. So observing the fact that you were treated is equivalent to observing one another draw from this thing, one another time period. And so the way I view what's going on here in this paper is essentially saying, well, this information is not very relevant if T0 is large, right? So we can ignore this, and we can learn about UI as an observed component from the outcomes only. And we will hope that this does not matter much. Okay? So that's the way I see this. Now, from the panel data perspective, and this is going to a slightly different literature than the one mentioned by the authors, this looks like a very fixed effect approach to me. Essentially, it means that, well, we have this unobserved confounding, but let's treat it as fixed parameters that we'll eventually learn fully. And as such, this is related a lot to what people have done in econometrics on MLE estimation for large T panel models. So there is a general treatment of such problems. So there is this paper by Emmanuel Ariane and Stéphane Bonhomme, an econometric, and the one message from that paper is that it actually matters a lot when you do this. Kind of, it matters a lot how you model which prior distribution you use, and they show which conditions kind of the prior distribution should kind of satisfy for this to work in general, right? So I think this is something that kind of has to be explored to understand whether kind of everything works fine in this kind of when you do this. Okay. The second thing is that kind of ignoring the assignment, I think, is not a big deal, right? In the types of settings that were considered in this talk, right? So because there are just few units and time periods that are treated, so kind of this effect that assignment matters is very weak. So probably it's kind of fine that you ignore that. But of course, like once you go to more general situations, it's not clear that that's the case, right? And one alternative is to model the whole thing, okay, including the assignment. And it's challenging because you need to take a stand on how it looks like, but there are general results in that direction. Again, from kind of this type of Bayesian perspective. And here's another paper by Emmanuel and Stefan on that. And one lesson from that paper is basically that the dimension of the unobserved components matters a lot, right? And here it corresponds to the fact that, well, these assumptions of how large the rank of this matrix is, or how much kind of persistence can we allow for in the unobserved components, it actually matters a lot. If you kind of start changing that, you can get very different answers. And in general, things are not identified. Okay, so I think this is another point that has to be made very clearly. Okay, so from a more kind of from a different perspective, like more related to the literature that was mentioned in the talk, like this to me looks a bit different than the synthetic control, not only operationally, algorithmically, but also kind of from the type of framework that we use when we think about it. So how do I think about synthetic control or other methods that are the same in spirit? Well, basically, kind of, we do not want to learn this and observe things, right? We do not care much about this low rank components or something else. We kind of want to find transformations of the data that difference them out, right? So you look at the synthetic control type of idea, you balance units in such a way that there is nothing left that creates differences in pretrends, right? And you can do this differently and using different types of estimators, but that's the underlying idea. And to me, that's more in spirit of more like traditional panel data econometrics, where you kind of fix things, you keep some things unobserved, right? So for example, you do not know the distributions of the unobserved components, you do not try to model the full kind of the full DGP, but instead kind of you find these transformations that kind of can deal with unobserved stuff. And to me, the advantage of doing this is I think it's kind of more transparent because you focus on a particular thing, right? So you just say, okay, I want to kind of make my units as homogeneous as possible, right? I want to kind of for periods as homogeneous as possible. I want to kind of balance this unobserved stuff. And kind of it feels like it's kind of easier to understand what's going on. And at the same time, kind of as far as I understand, kind of you need fewer assumptions to actually do that. So in some sense, it's more robust. Of course, there are disadvantages, and those were mentioned in the talk. It's very hard to generalize it because every case is a special case. You do not get the full distribution, which is always a kind of problem. And of course, inference is super hard. And I think this is, to me, this is the main advantage of doing things in the Bayesian way, right? Because you automatically get these posterior distributions, and that's kind of can be used to quantify the uncertainty. Okay, so I think that's the kind of the trade-off that drives this whole thing. So going forward, I think this is super interesting, kind of to understand when this kind of ideas that were put forward in this paper, especially kind of in terms of the assumptions, this assumption 4 that was made that the latent structure can essentially be learned. And to me, that's equivalent to the fact that the assignment can be ignored, is kind of when we can make that assumption safely, right? What exactly it means, right? So which are the models, which models will satisfy this kind of, at least in some sense. So this is one thing. The second thing is I think that the assignment model is an important component of all this. And I think that we should try and use domain knowledge. So this can be in the political science applications, or this can be in economic applications. Typically, the assignment is a choice of some kind, and we can use our ideas of what drives choices to model that thing, and go beyond just strict or sequential exogeneity under unobserved confounding, but actually kind of try and model that. And I think there are some steps in that direction, but I think this is something that is super exciting, and I think that more work should be done on that. Also, kind of, if you start thinking about the types of kind of these models that were put forward, it's a bit kind of asymmetric, right? So there's this super flexible model for the baseline that is used in this paper, but kind of it is still a model, and we kind of use it, kind of we can criticize it, but we think that's a good model. But then we want to be completely flexible about the effects, right? We want to say, okay, anything can happen. And maybe if there are just few truth units and time periods, that's fine, right? But with more general designs, if we go beyond just having 50 countries, but actually kind of having a lot of units, and some of them are treated, some of them are not, and some periods, then kind of it's more natural to me to do things more symmetrically and actually think about the types of effects we might be looking for. So we know from the cross-section settings that typically treatment effects are small. So it means that we can learn a lot from the data, and kind of not just modeling the baseline, but also by modeling the outcomes for the treated units as well. So I think this is the kind of my comments. And I just want to say again, I think this is a super exciting paper. I think this is super exciting kind of direction, and I want to see more done in this spirit. Okay, thank you. I'll just stop sharing.
Thanks for the great discussion, Dmitry. Jin or Yiqing, do you want to respond quickly? You have to unmute yourself. We can't hear either one of you currently. Yes, now we can hear you.
Shane, there are two questions in the Q&A. Maybe you can answer them based on the prior one on the prior.
Perhaps you want to read the question to Jin that you want.
Oh yeah, so it's not clear to me which functional of the observed data corresponds to target parameters. Do you have expression of the estimates as the function of the law of the observed alone? That's one question.
Which function of the observed data corresponding to the target parameter? The parameters. Do you have expression of this function?
I'd like to thank Dmitry for the comments. Those are really helpful. Thank you. The reason why we struggle to model the assignments is because there are just only one treated unit. It's very difficult to do with this setting. But we're actually looking for better examples where we can more successfully model the assignment mechanisms. I think that's certainly the way to go.
Okay, yeah, so do you want to answer to that one question? We're also running out of time, but perhaps a quick answer. Still fine. No? Okay, then I think it's time to start wrapping up. If you have further questions, yeah, we encourage you to send emails to the co-authors. I'm sure they are happy to and have more time to answer there. First, thanks to our volunteers today. So thanks Jin and Yiqing for the fantastic presentation, and Dmitry for the great discussion. Next week, we have two speakers, so we're deviating slightly from the format. We have Georgia and Lihua, Georgia will talk about causal interference with spatio-temporal data, estimating the effect of airstrikes on insurgent violence in Iraq. And we have Tsinghua talk about conformal inference of counterfactuals and individual treatments effect. We're very much looking forward to that talk. Until then, we all hope that you stay safe and hope to see you next time. Thanks all for joining.
Thank you. Thank you so much.
Thank you.